Well, welcome, physics students, to a brand new unit on electricity and magnetism. You can follow along in the notes handout that I've given you, and the first part of our adventure deals with electrostatics. And we're going to get into the concept of charge today. So let's begin.
No, me take over. You not know what you talk about. Give me a microphone. Okay. Now, I spend little time with you today. First, talk about that wacky, crazy dream I had. Oh, now this is what happened in my dream. Oh, I dreamed that like a universe like this, but much stranger. Yeah, like a force like gravity. But not like gravity. No, it's different. Billion times stronger. Oh, big, strong force. Incredible. Oh, you not understand what this mean. It mean like if this force was so attractive like gravity, oh, it crush everything. Oh, in like fist. Oh, super powerful. Oh, no kidding. If this force would not instead repulsive, oh, what happened then? Let's see. Anyone know what happened? Oh, Scooby-Doo, come tell me what happened. Shaggy? No, it's me. You know me. Oh, listen, what happened if it was repulsive? Will it shrink? Will it stay constant? Will it expand? Oh, very good, Scooby. You're so smart. Smarter than a little baby at home. You expand and cool into death. Quiet, uneventful death. Oh, not so good. No. So what if force were both like kind of attractive and like repulsive? Oh, yeah, perfectly mixed. Cool, yeah, you're balanced. Oh, well, the odds of that? Oh, so slim. But imagine universe be like universe like exact like when we live in right now. Yeah, well, it's a force, same force we call electrostatic force. It's a billion times stronger than gravity. Yeah, very strong. It equally balanced between attractive and repulsive. Oh, yeah, perfect. Oh, it's incredible. And this is the universe that we live in. Oh, we learn about this universe now. We continue. Excuse me,
Could I please talk to my class?
oh, no, sorry. Okay.
To the lesson. Now, here's the deal. We learned a lot about mass all last year and even dealt with it some of this year. And I never told you what mass was. As a matter of fact, you never asked me what mass was, and I'd have a very hard time explaining what mass is because it's kind of the basement level of physics, and there's nothing underneath it to explain it with. So you may have realized that we dealt with mass pretty much throughout the year in kinematics. We dealt with mass moving. The concept of inertia deals with mass. Gravitation deals with mass. Momentum deals with mass. Kinetic and potential energy deal with mass. And we're going to move away from mass as our focal point, at least, in this unit of electricity and magnetism. And our new focal point is going to be charge. And in much the same way I didn't tell you what mass was, I'm not going to say exactly what charge is. I'll describe what it does, but not exactly what it is. So if you had some experience in chemistry, a bit about charge. You know that we have positive and negative charges. But are they really positive and negative? If you took the microscope to them, or the electron microscope to them, or would you actually see little positive and negative signs on them? Not really. Ben Franklin is the one that we can thank for these conventions of calling them positive and negative. He could have called them Fred and Sue. He could have called them black and white. But they definitely have opposite sorts of characteristics with each other. They have very different characteristics with each other, and they were just named positive and negative. Now, you might know the names of these positive charges. We've called them protons, and the negative charges, we've called them electrons. And where do they hide out? They hide out inside of the atom. And so here we have a diagram of an atom, and we see that there's positive charges hiding out in the center here, in the nucleus. And there's these neutral charges. They're not really charges at all. They're just neutrons. They're neutral in charge. Also joining them inside the nucleus. And on the outer part of the atom, we have the electrons. All inside the atom, ATOM. A tiny piece of matter. But that's not really what it stands for. It's a Greek word for the smallest indivisible part. So if you have some experience in chemistry, you're familiar with the setup of the atom, and you're familiar that the nucleus is really hard to break apart. As a matter of fact, it takes an incredible amount of effort to do anything separation-wise between the particles in the nucleus, because the strongest force in the universe holds them together, called the nuclear strong force. Whereas the electrons, which are much, much more weakly held to the atom, are relatively easy to mess with, to remove, or to add more of. And we'll get into more of that later on. You may be familiar with this, that the positive and negative charges, they have an attractive force between them. Whereas like charges over here, negative on negative or positive on positive, they have a repulsive force. So opposites attract is what we say. Over here with the positives and negatives, you see the opposites attracting. Now remember, this force is a billion times stronger than gravity. So if you put a gravitational force up against an electrostatic force, the electrostatic force would win a billion times over. Now, I want you to remind me when we get back into class to do a demonstration with electricity and hair. And I'm probably going to pick on someone with long hair, which most likely is going to be one of the ladies. So ladies, if you can please remember, do not use conditioner. It will mess up the experiment. Now, some basics on charge. This is where we'll wind it down. The unit for charge is the coulomb, last name of a fella. And the symbol for coulomb is C. Now, if we were to actually have a coulomb of charge pass through our body in a relatively quick amount of time, we probably would never recover from that. A coulomb is a massive amount of charge. Think back to the basic quantity last year when we dealt with mass. And a kilogram was the unit for mass. Well, 1 kilogram we could hold in our hand. It's not a big deal. 1 coulomb passing through us of charge is a humongous amount of charge. Typically, the kind of charge, the kind of quantity of charge that gives us that electrical shock tingle that feels maybe not so great, but also not so bad, is 10 to the minus third or smaller coulombs that we may complain about, but we'll definitely be able to get back up from. So 1 coulomb is a massive amount of charge. In the Regents reference table, you'll find that 1 coulomb is the charge of a heck of a lot of electrons. If you look at that quantity of electrons there, 6.25 times 10 to the 18th electrons. How big is that? Well, go ahead and take the decimal point and move it over to the right 18 places, and that's how many electrons you'd have to make up a coulomb. That's a lot of electrons. We can also say that coulombs can have a positive quantity of charge or a negative quantity of charge. And if they have a positive quantity, that means that they're made up of an excess number of protons. And if they have a negative quantity of charge, that means they're made up of an excess number of electrons. And lastly, we'll say that Q is the symbol for charge. So you might see charge written as Q equals 15 coulombs. It's not bad for NICEAG, but it's real bad for a human being. So get all these details down, and we'll be chatting about them in class. Remind me to do a demonstration with the Van de Graaff. That's it for now.